particular, we will use Morse theory to obtain handle decompositions. For manifolds. Okay, so here's the idea. There is a connection between Morse theory, handles and surgery. That's the point of this lecture. Namely, if we have two real numbers a less than b, and they are regular. I'll explain what this means in a moment, but I'm sure you probably all already know regular values of a Morse function. Function to the real line. Then, if we look at the pre-image of the interval from a to b, this gives us a cobordism. Of m-1 manifolds. In particular, if all the points in A, B are regular, then the cobordism is a product so we deduce that the manifold F inverse of A is diffeomorphic to F inverse of B, and if they're not all regular, if there is a critical point, I should say non-degenerate, then we get an elementary cobordism, which is attaching one handle from F inverse of A to F inverse of B. Okay, so this is the idea. So from now on, let's F a map from M to the real line, be C infinity. Although strictly speaking, I think C2 is sufficient for most of this to work. So, definition, a regular point of F is an X in our manifold such that the F of X is a linear map of maximal rank. So this holds more generally for maps between smooth manifolds, but as we're just considering a map to the real line, we're only considering to R. So for the respect to local coordinates, not all the derivatives vanish. If they do all vanish, we say that it's a critical point. Again, with respect to local coordinates. And then the images of these points are called regular if all the pre-images are regular values, and critical otherwise. So a regular value is a point in image, so y in R, such that x inverse for all x in the inverse x is a regular point. And then it's critical otherwise. Okay. So now we can distinguish between critical points by whether they're degenerate or non-degenerate. So we say that a critical point is non-degenerate if the Hessian matrix again, we've taken local coordinates xi is invertible. And in the case that it's non-degenerate, we say, okay, let's just do part 1, part 2. We define the index in of x. Non-degenerate critical point is the dimension of the negative eigenspace. Of h of x. Okay, so we'll see a couple of examples in a moment. Sorry? Maximal negative, yeah. So 3, we say that f is a Morse function if all the critical points are non-degenerate. Okay, now 1 or 2 examples. Most good examples are all height functions. We have so Now if we put the cylinder on its side like this, and then map to the real line and measure the height, we get a whole line of critical points, both along the top and along the bottom. So we get now, so we'll see in a moment that non-degenerate critical points have to be isolated. So immediately from this fact we would know that these critical points are degenerate, and so this function is not a Morse function. But we can also look directly just at the function. Don't worry, I won't go into too much detail. And this, if you take local coordinates around a point up here, say, this is what the function looks like, and then you calculate that the Hessian, so if I took this as height 1 and t is the variable going across, you get 1 minus 1 and the rest series. So this is corresponding to the fact that if you go up in this direction, you go down, and if you go up in this direction, there's no change. So this is the minus 1 in this area. So this is not invertible, so it's not, it's degenerate. Okay. Second example, almost the same, just the sphere with a height function. This time we get a Morse function, and we have two critical points. We have this maximum and this minimum, and if you calculate Hessians at the top, you get there's two negative eigenspace directions, down that way and that way, and at the bottom you get two positive directions again. So this means that this point has index 2 and this point has index 0. And this is